No, yeah, it's, yeah, sometimes just focus. Yeah, welcome to the last session of this year's GCM. So this session is intended to be a little bit more of an interactive workshop style session. We'll start with hearing 4 lightning talks, 5 minutes. And I would like to also keep the questions directly after the talk to rather kind of minimal questions about understanding, stuff like that, so that we have a common discussion that starts with the talks. And yeah, it should be a free session. So if there's a need for breakout groups or something, we can do that. The talks are intended to inspire us, but we can also talk about the talks we heard earlier. So it just should be a session where we can think about interesting ideas for future research, maybe start cooperations, use the time, but first enjoy the lightning talks. And Marc is going to start talking about functional programming language for interaction.
Yep. Thank you very much.
Stage is yours.
5 minutes or less. Here we go. Luckily, you've already heard about interaction nets for Ian, so I can skip the first section. But important points to remember, in case you've forgotten anything, is we have a finite set of user-defined nodes, and we have ports connecting those nodes together. One of those ports is distinguished as the principal port, shown with an arrow here. And those are important because when those 2 of those connect, that actually defines the rewrite rule. And again, we move from two agents connected here to any arbitrary net here. The important point is that we have the interface with the rest of the net remains the same. What this means is not only is this system Turing complete, but it also can be parallelized. And also this interface actually enforces garbage collection and memory management onto the system. So you saw addition earlier with unary numbers. We're going to use unary numbers again, but this time it's going to be multiplication. So in this case, how does multiplication work? Well, again, 2 cases, we multiply by 0, we get an output of a 0, but here comes the garbage collection bit. In order to keep the interface the same both ways, we need to then erase whatever the other number was. And then, of course, the second case is we're multiplying by some number greater than 0, some successor of something of 0. And in that case, we're going to use a recursive addition approach. And again, we have the memory management here where we need to copy one of the inputs in order to do the recursion. So this is how we will draw this out as interaction nets. But what if we actually want to start programming with this? Well, this has been done, and we have explicit textual syntax that has been used. But as you see here, we have to start labeling everything. So suddenly, things that didn't have labels on them, everything's got a label on it. We've got this rather sort of cryptic syntax because everything that's going on, we need to explicitly state. So we need to explicitly have some syntax for this is a live pair with 2 principal ports. We need to explicitly have some other syntax for saying we've got principal ports coming on the right-hand side. And then for everything else, we need to be, again, explicitly stating that something's going on and putting letters or names or whatever on all of it. So this will work, obviously, as a very, again, explicit description of what's going on. And this is great if you're a computer, and this is running on the system that Ian mentioned earlier. But if you're a human being, of course, this isn't quite so nice. We all know that human beings like to program with functions. So can we rewrite this in a more functional style? And the important point here is that what we're doing is we're still describing the rules and the nets, but we're doing it in a functional way. We're not writing a functional programming language and compiling it, but we're doing a description, but just in a different format. The nice thing is once we start thinking about things as functions, we can take away some of this explicit stuff that we had to put in before. So for example, if you have a function, multiply 0 by y, you have to have an output, in this case 0. The fact we know there has to be an output means that the compiler can say, well, look, I need these nodes at the top to be connected to something, so I need some output ports. The fact that we're going to have live pairs, we know we have to have two principal ports connected in order to have a regex. Well, let's just ensure that that's put down as the first input into the argument list of the function. Yeah, we don't have to use a special syntax. We just put it in the right place. And then when we actually have some things that may not be functions. So here we have, again, the arrays. And the arrays is doing what you'd expect. It's working its way through that list of successors. When it comes to a 0, the two match, they annihilate each other. They disappear. There is no output. So in that case, that is not a function. So what we do here, we use a sort of foreign language interface type idea. We put the curly brackets in, and then we use the other explicit text language to actually define what is happening. Overall, when you look at this, you can see here to some other examples. It looks very much like a functional language, but again, it's actually describing the set of rules that are going to be used in some net that's done. And this is actually the sort of where we are at the moment in terms of actually implementing all of this, so an addition length and a sort of a bubble sort on a list. The ongoing work we're working on at the moment, I won't go through all this, but you can read it. Is really looking to extend the expressiveness of the language, so it's going to be easier to do more than just some sort of toy examples in there. But this is as I say is sort of work in progress. I look forward to coming back next year, telling you about implementing this. Thank you. Any simple questions will be answered in 10 seconds.
Do you have to play all the functions?
Not yet. Coming. Next year. This time next year.
Other questions?
So this erase stuff is actually a bit like a, I don't know, side effect. It's not completely functional.
No, exactly. So that's why we're having to sort of slightly escape from the pure functional way of because what we are trying to use functional style in order to describe interactions, but of course the interactions themselves may not be functional. You know, the interaction net has no concept of function in it. And so there are some cases where you may have to
I guess you could just ignore the stuff below erase if there was no sharing, but you may have others.
Right.
Okay.
Right, exactly.
Thank you very much. And then we are going to have 3 talks somehow connected to the idea of graph languages, generating graphs or recognizing whether or not a graph belongs to a given language. And we are going to start with Marc.
Can you hear me?
Yes.
And I share my screen.
Yeah, go ahead.
Can you see my screen?
Yeah.
Okay. I can start if you wish.
Go ahead.
Okay. Hello, everybody. I cannot see you, but hopefully you can see me a bit. So this is joint work together with Frank and Berthold, who are also in this Zoom meeting. And as always, if we give a talk, it's on parsing, but this time it's not directly on parsing, but on recognition. So what is the definition? What is the difference between recognition and parsing? Well, recognition uses finite automata, whereas parsing uses parsers. So what is the difference here? So the idea I want to show you here is goes back to an idea of Engelfried and Verreken to interpret regular expressions as languages of graphs. And I show you with a very simple example. Look at this simple graph or language of graphs here. This language consists of stars consisting of as many A edges as you wish, and exactly one B edge. So what we consider not just only graphs, so we consider graphs, hypergraphs, in fact, with external nodes. So in fact, we distinguish between a front interface. These are some of these nodes here. in this case, it's just one node, but it can be any number of nodes. And we also have a rear interface. In this case, it is empty. Why are we using this? It will become clear in a moment. You can, if you look at such a graph here, you can see that it can be decomposed into single edges. And you can see that you have a sequence of very simple graphs consisting of just one edge. And each of these graphs has a front and a rear interface. And you can see that you can connect these graphs. Connecting means that you merge, for example, here, this front node with this rear node. So in fact, you merge this node and this node. So you see that this concatenation of these graphs is the same as this graph here. And now this was the idea of Engrid and Verreken. You can consider any symbol. Let's say here we have the symbols X and Y, and the meaning of the symbol X is just this simple graph, and Y is just this simple graph. So you have a concatenation of interpretations of these symbols, and now you can lift this interpretation to sequences of symbols, meaning strings. So you have a string consisting of X and Y's. So this is just a member of this described by this regular expression X star and then followed by Y. So you have an interpretation of the string as a graph. So why are we? This is the idea, and what we now look at is, if you look at regular expressions, you always can define a regular expression by a finite automaton. And so this is a finite automaton for this, just this regular expression, and now you can replace the symbols by the interpretations. Now you have a finite automaton which describes, well, all graphs which can be represented the way as I have just described to you. So, and we are thinking about recognition. So you can use automata for creating graphs, but also for recognizing. So what you can do, for example, you would like to know whether a graph belongs to the language. So this means you have an input graph. Here's a particular graph with 3 A's, and you would like to check whether it is recognized with this graph, with this automaton, and it is immediately clear that it can be recognized. You just consume all the different A edges here in this loop transition, and at the end you consume this B edge, and at the end the entire input graph must have been consumed. So this is very easy in this very simple example, but in general, of course, the automaton is non-deterministic. So you can come to the idea, okay, we use this the usual power set construction, what we have done, but the problem is that even the power set construction doesn't remove the non-determinism. You just you can see it in this example here, which A edge is consumed first, which is the second, which is the third one. So in this case, it doesn't matter in which sequence it is these edges are consumed, but in other cases it might can make a difference. And for that, we have identified a subclass of languages by looking at these automata, where this recognition can be done without backtracking. So as soon as you decide for one edge which is consumed, you know that this is the right one. So, and we do this by two certain conditions. We need a look ahead, which looking into the graph to decide which of the transition to use. Here you can see this. You use only this transition here to the terminating state if there's no longer an A edge. So this is a look ahead, and we need also a certain property that we don't run into a problem if you decide for the wrong edge for consumption. So we just in this way we devise finite automata for efficient graph recognition, and we would like to use it, for example, for checking graph conditions, for example, for controlling parsers or anything else. And you would also look into different kind of formalisms where also nodes can be identified. And of course, at the end, I just want to point out that this using automata for graphs is not new. For example, Sander and Barbara and also others have used these automata, but just for assembling graphs, not for recognition. And Brandenburg and Scodinis also have used finite automata, but only for node replacement. Thanks for listening.
Thanks, Marc. Are there any short questions?
One obvious question is, what do you know about the power so far of the method? Or what graph language can you specify?
Well, of course, so all the languages of graphs that can be represented by, let's say, linear hyper-edge replacement grammars cannot be recognized, because this thing with this free edge choice property must be true, and also, oh, sorry, here, and also the look ahead must be possible. So this is, of course, connected to our previous work with parsing of hyper-edge replacement grammars, and there's also this restriction. So, but in this case, so this is not finished work so far. So we are hoping that for this restricted kind of formalism, it is possible to easily check this free edge choice property. The look ahead condition can be easily checked. So this is essentially the same idea as we used for parsing general hyper-edge replacement grammars, and this is also related for the well-known LR parsers by Donald Knuth for the string case.
Thanks.
Yes, very good. Now there are two talks coming up about generating or sampling of graphs. The next talk is given by Justin. It's also a remote presentation. Justin, could you unmute yourself? We see your slides, but we don't hear anything. Hold on a second, please. He's still Cheryl.
Okay. Hello? Can you hear me?
Yeah, now we hear you and see your slides.
Okay, great. So this is going to be a slightly different type of presentation, but I hope you can follow me. So yeah, what we're going to be talking about is our kind of conceptual work of how we can efficiently sample from the Boltzmann distribution with graph generative models using constraints. So I'll try to kind of give the background about this really quickly and what conceptual framework we're dealing with how to do this in a more precise and efficient manner. So when we're dealing with computational chemistry, what we are often interested in is sampling from the Boltzmann distribution. And so this distribution represents the equilibrium distribution of states that a system will naturally gravitate towards over time. So despite how important it is, sampling from it is often really difficult. This is often due to the partition function, which is basically an integral over the state space. And in practice, calculating the partition function is usually intractable. So what we're doing is we're looking at a class of models called the noise and diffusion probabilistic models. So if you've seen the AI image generative models in the news recently, that's mostly what these are based off of, that and transformers. But we're using these models to generate samples from complex probability distributions. So in a very high level framework, these models are given a initial probability distribution, usually a series of Gaussians, So it's a very, very simple distribution. And through a parameterized neural network, you iteratively modify this distribution to be something more complex, like the Boltzmann distribution. So what we've shown here is that we've derived an expression, a constraint expression, for continuous graph generative models to formally sample from the Boltzmann distribution, even when the data distribution doesn't necessarily come from the Boltzmann distribution. So just a really quick overview. The Boltzmann distribution has this principle of maximum entropy. This is how it's defined, and it's subject to the constraints that we impose on the system, which in this case is that the average energy of the system has to be some specific value u, and where h is the Hamiltonian of the system, and then to find the distribution that maximizes the entropy while maintaining this energy constraint. Lagrange multipliers, a very common procedure in linear algebra, for instance, are used. So by taking the derivative of this Lagrange multipliers and setting it to 0, we get the expression for the Boltzmann distribution. And this, in a sense, defines what the Boltzmann distribution is. But what we want to do is how do we incorporate these kind of structures, that we get from these constraint expressions, into more general generative models. And so just to give a quick overview of what these general generative models are, is that they're often based on stochastic differential equations. So in this case, D stands for some diffusion coefficient, which determines how rapidly the system state can change. And B represents some Brownian motion, which is some random process that models the continuous random fluctuations of the system. And then P of T is the probability distribution which you're aiming to model, in which we hope will eventually sample from, which we hope we can obtain samples from the Boltzmann distribution. And then X in this case is some sort of set of molecular coordinates. So when one introduces constraints into these equations, we get this new term, which is this projection operator. And this projection operator effectively removes the components of the Brownian motion onto the direction of in the direction of the constraints. And so it ensures that the random fluctuations don't violate some number of constraints. And so these equations were formalized with geometric constraints, but we are looking at how to use these for global properties of the state space, like the densities. So to formalize these Boltzmann constraints into our generative model, we noticed that in neural networks that model some sort of dynamics, like in our case, molecular dynamics, we can interpret the Hamiltonian of the system as the negative log likelihood of the target distribution. So here the P of T represents the density at some time t, which are in the generative process. And if we want to impose the Boltzmann distribution, we can just incorporate these constraint functions into the generative process of the probabilistic denoising diffusion process. And what we end up with is we get this constraint matrix that replaces the projection operator that we saw in the previous equations. And this matrix represents the second order partial derivatives of the log probability, which captures how sensitive the system is to changes in different directions in the state space. So this ensures that the diffusion process respects the constraints encoded by the Boltzmann distribution. And so how do we ensure that the dynamics of these generative process are constrained at each iteration, at each generative step of the diffusion process? Is that at each step we essentially have to solve for the Lagrange multipliers, and it basically and so we can use some iterative update mechanism and the gradient of the constraint function to update the coordinates at each time step. So we can then update the state of the system by incrementally satisfying constraints by solving the Lagrange multipliers at each step. And the Lagrange multipliers in this case simplifies to just determining the magnitude of the corrective force applied at each step. So with this at iterative update scheme, we can accurately, or at least hopefully accurately, sample from the Boltzmann distribution and concurrently satisfy other, for instance, geometric constraints. So yeah, we have a conceptual framework of how we want to approach the problem, and there's some useful software frameworks that we can try to implement this in, so that would be, I guess, the next step, how we can really get, how we can show that the samples from the Boltzmann distribution, even when the data that we train the neural networks on, it could be any type of molecular dynamics data set that doesn't necessarily have to come from some Boltzmann distribution. So thank you.
Thank you very much. What questions? One question from my side, I'm not completely sure if it might better fit to the discussion afterwards, but is there some kind of logical formalism with which you can also express the constraints which you are considering? I mean, the constraints were given as stochastic differential equations. Is there some connection to the known logic on graphs?
I'm not sure. Yeah, maybe that's something that, yeah, actually other people could guide me towards what are useful things to look at in that respect. But I'm not aware of anything, though. Okay, thank you.
Further questions? Then we will have the last lightning talk before we start with our discussion. Federico?
You have those slides in there already?
They should be
Open to this one. Now it should work again. Okay.
First of all, this is the percent of the GCM ago. What we do? We generate graphs. We give an excellent method to generate specified graphs from specified aggregate represented language. So the user specified the language, and if the grammar represented language is non-ambiguous, the generation is also done before the data. So in contrast to the conventional method, which usually you have a set of nodes and a way to add the edges, here we give the user the power to fine-tune their domain. Basically, they specify everything in the language. And also they can create a large and unbiased set of data. Because I think that since our method is efficient and we can create the set of data for testing structures. Okay. As an application, that's from network design to photography, where we start from. We start from the Markson J method 24. Basically, what Markson did to offer a method to uniformly generate strings from context-free languages. What we did is to create a particular Chomsky normal form to adapt to the and we give the definition of ordered derivation trees. Basically, this shows the uniqueness of the derivation. This is an example of choosing Berthold grammar. And this is an example of our ordered derivation tree. Our method is divided into parts: a preprocessing phase and a generative phase. The preprocessing phase takes all the information from the grammar, and the generation phase recursively generates the hypergraph for this information. This is an example of the tables from the preprocessing phase. You see the size of the hypergraph we want to generate. Just I think we use the grammar from the user and the size of the hypergraph to generate. So this is the size. These are the non-terminals in the production. These are actually the number of subgraphs of given size we can generate. This is a full example of a generation phase. We're starting from the hand of the non-terminal. We recursively generate all the hypergraphs. This is the same graph how we do it? First, we decide which production to apply, and then we decide the phase. So, how big is the spike hypergraph from each non-terminal that we created, or simply we create the terminal and we stop this branching of the generation. So, our results, we give a theorem of uniformity. We say that given a grammar and the size of the hypergraph we want to generate, if the grammar is non-ambiguous, the algorithm generates the hypergraph uniformly random. And also a theorem of complexity. We say if the hypergraph is generated uniformly random, this is also generated for that time. To work, we are actually working on the string graph generation. So the application of our method to string graphs, so can generate strings from context-sensitive languages or even inertly ambiguous context-free languages. And we are also working on generation of hypergraphs with interleavings. Also, working in the integration of executive languages, we have time generation for ambiguous grammars. Also, the application we say about test data. And the last one, how our ordered derivation tree applies to parsing hypergraphs instead of the generation. So all the way around, which is the advantage of the ordered derivation trees for the problem parsing.
Questions for Federico?
The role of the non-ambiguity of the grammar, guaranteeing the uniformity of the, I understand that if it is ambiguous, you can generate the same graph with two different derivations, therefore it is more probable that it appears. It's simply this, the question of there is something more.
No, very simple. You can use this same method on ambiguous grammar, but the uniformity is not guaranteed.
Das ist schon genaue Form von Image Replacement.
This is one. Every rule, introduction, can have two non-terminal averages or one terminal average.
This is always possible. Even if there are large clicks in the car. If the right-hand side of the wheel has a large click.
Yeah, because you
can even then you can.
You can just remove one average once. So if
You should perhaps also say, so the one we use in the Chomsky normal form is similar to Engel's Chomsky normal form. And he has it in its handbook article.
The difference with the angle fit that he allows to have just one terminal hyperage on the right hand side. Instead, this one, since non-contractive, have to place two non-terminals. Otherwise, you cannot guarantee the termination of the argument. Because we also give all the rules for creating the choosing platform, and we also guarantee the termination of the argument. So the full paper is everything.
And before we start the discussion, one thing I forgot was the card found, some kind of wooden card, which is maybe an entry card in the hotel room. Not